Hello everyone, my name is Mohammed Zainuddin and today I'm gonna give a presentation on weighted graph problems. So the first slide where we go through the introduction, key concept, minimum spanning tree, shortest path algorithms, network flow problems, practical examples and applications, and in the last will we have audience engagement and conclusion. In the introduction of weighted graph problems, we will have brief overview of what weighted graphs are and why they are important. And their key concepts will be fundamental elements and terminologies related to weighted graphs. And how minimum spanning tree explanation of what an MST is and how it can be computed using different algorithms. And how shortest path algorithms methods to find the shortest path between nodes in a graph and network flow problems discussion on how to determine the maximum flow in a network. Practical examples and application where real world scenarios where these graphs algorithms are applied. And we have the interactive segment to involve the audience in the discussion and the conclusion, summarization of the presentation and recommendation for further reading. Where the slide 3, where we have the definition for a weighted graph, is a type of graph in which each edge has associate numerical value called a weight. These weights typically represent cost, lengths, or capacities. And their importance, are typical. Weighted graphs are critical in various applications, network routing, geographical mapping, resource optimizations. Network routing find the most efficient path for data packets. Geographical mapping calculating distances or travel cost between location. Resource optimization allocating resources in a way that minimizes costs. We have key concepts in which we have edge and weights, path and cycles, graph representation. Edge and weights, basic buildings blocks of weighted graphs, connection between pairs of nodes. Weights, numerical values assigned to edge indicating cost, distance or capacity. In path and cycle, path a sequence of edge connecting two nodes, where the cycle a path that starts and ends at the same node. Graph representation. How graphs are sorted, adjacency matrix and lists, methods for sorting graphs. Adjacency matrix, a 2D array where the cell at row I and column J indicates the presence and weight of an edge between nodes I and J. Adjacency list, a list where each node has a sublist of nodes it is connected to along with the weights of these edges. And we'll move to next slide, where we'll have the minimum spanning tree. Definition: a subgraph that connects all the vertices together without any cycle and with the minimum possible total edge weights. Kruskal's algorithm, a greedy algorithm that builds the minimum spanning tree by repeatedly adding the smallest edge that does not form a cycle. Prim's algorithm, another greedy algorithm that starts with a single vertex and grows the minimum spanning tree by adding the smallest edge that connects the tree to a new vertex. We'll move to the Kruskal's algorithm's steps, where the step 1 sort all edges in increasing order of their weight. where the second step, pick the smallest edge, check if it forms a cycle with the spanning tree formed so far. If not, include this edge, else discard it. In the step 3, repeat until there are V1 edges in the spanning tree. V is the number of the vertices. Continue adding edges until there are V1 edges. We'll move to Prim's algorithms, where their steps start with a single node. Grow the minimum spanning tree by adding the smallest edge connected to the tree that does not form a cycle. Repeat until all vertices included in the tree. The shortest path algorithms. Definition for that: finding the path between two nodes such that the sum of the weights of the edges in the path is minimized. Descartes algorithm. Shortest path algorithms to finding the path between two nodes such that the sum of the weights of the edges in the path is minimized. Dijkstra's Dijkstra's algorithm efficient for graphs with non-negative weights. It maintains a set of nodes whose short distance from the source is known and expand this set by finding the shortest distance to the remaining nodes. Bellman-Ford Algorithm, capable of handling graphs with negative weight, it relaxes all edges repeatedly to find the shortest path, ensuring correctness even when negative weights are present. The next slide will show the network flow problems. Problems involving the calculation of the maximum possible flow in a network from a source to a sink. Ford-Fulkerson algorithm uses the concept of augmenting paths to incrementally increase the flow until no more augmenting paths are found, achieving the maximum flow. Where the next slide shows the real world scenarios like internet routing and the problems where we face determining the optimal path for data packets to travel from a source to a destination, and the solution using algorithms like Dijkstra's to find the path that minimize latency or maximize bandwidth. Road network and the problems find the shortest or quickest road between two locations. And the solutions are applying algorithms like A or Dijkstra's to calculate the shortest path considering the distance or traffic. Supply chain optimization problem: reduce transportation cost for delivering food goods. Reduce transportation cost for delivering goods. Solution: use minimum MST algorithms like Prim's or Kruskal's to design cost-effective delivery routes. We'll move to the next slide where we have hands-on examples. Design a minimum spanning tree for a network scenario connects a set of computers with the minimum total capable. Computers with the minimum total cable length tasked to find the minimum spanning tree for the network solution. We have graph representation, represent the graph as a graph where computers are nodes and possible connection are edges with weights. Algorithm selection use either Prim's or Kruskal's algorithm. Step-by-step solution. Prim starts from an arbitrary node. Grow the MST by adding the smallest edge connected to the tree. Kruskal's sort edges by weight and the smallest edges to the MST if it does not form a cycle. Result display the minimum spanning tree and total cable length. In the audience engagement, will we have questions like what is a weighted graph? A weighted graph is a type of graph where each edge or arc is assigned a numerical value called a weight. These weights represent some metrics such as distance, cost, time associated with traversing the edge. Weighted graphs are used in various applications where the relationship between the nodes have different significance or cost associated with them. For example, in a transportation network, nodes could represent cities and edges could represent roads with weights representing distance between cities. In a social network, nodes could represent individual and edge could represent relationship with weights indicating the strength or frequency of interaction between individuals. The difference between Kruskal's and Prim's algorithm. Certainly, both Kruskal's and Prim's algorithm are used for finding the minimum spanning tree for a graph, but they achieve this in slightly different ways. Kruskal's algorithm is a greedy algorithm that works by selecting edges in increasing order of their weights and adding them to the MST if they do not form a cycle. Sort all edges in a graph by their weight. Initialize an empty graph as MST. Third, as edges to the MST one by one from the sorted list, ensuring no cycle are formed using a union find data structure to manage connectivity. Whereas the Prim's algorithm is also a greedy algorithm, but it starts from an arbitrary vertex and grows the MST by adding the cheapest possible connection from the tree to a new vertex. And its process starts with an arbitrary vertex and include in the MST. Grow the MST by adding the cheapest edge that connects a vertex already in the MST to a vertex not yet in the MST. Repeat until all vertices are included. Whereas we'll discuss the key differences edge selection. Kruskal algorithm selects edges to add to the MST based on their weights and check for a cycle using a union find structure. In summary, both algorithms are greedy and find the minimum spanning tree of a graph. Kruskal focus on edges and avoid cycles using a sorting mechanism, while Prim's focuses on vertices and uses a priority queue to efficiently find the shortest edge connecting the MST to a new vertex. How does Dijkstra's algorithm handle negative weights? Descartes' algorithm is designed to find the shortest path in a graph with non-negative edge weights. If there are negative weights in the graph, Descartes' algorithm may not work correctly or may produce incorrect results. Greedy approach. Descartes' algorithm works by always selecting the vertex with the smallest tentative distance from the source vertex at each step. This greedy approach assumes that once a vertex's shortest path is determined, it does not need to be revisited. No negative edge relaxation. The algorithm relies on the property that once a vertex is marked as visited, that is, its shortest path is determined, it will not be revisited. These assumptions hold when all edge weights are non-negative because when the shortest path to a vertex is found, No shorter path can exist through the vertex. However, with negative weights, this assumption breaks down because a shorter path might be founded by revisiting a vertex due to negative weights, which reduce the path length beyond previously known distances. In summary, Dijkstra's algorithm is not suitable for graph with negative weights due to its greedy nature and the potential for incorrect results. Algorithm specifically designed to handle negative weights like Bellman-Ford or fluid Warshall should be used instead. In conclusion, further reading books, Algorithm designed by John Kleinberg and Eva Tardis. Introduction of Algorithm by Thomas Corman Charles E. Online resources we can find on Greeks for Geeks Graph Algorithm. Thank you for your